In this lecture, we'll discuss spherical coordinates, which is another way of extending polar coordinates to 3 dimensions. Let's start by looking at a point in 3 dimensions with Cartesian coordinates x, y, and z. And let me remind you what the the cylindrical coordinates were. So remember that we looked at the shadow of this point in the xy plane. We let theta be this angle here, and r be the distance from the origin to this point down here, which is really the point x, y, 0. Now with spherical coordinates, instead of looking at the distance from the origin to the shadow, we're going to look at the distance from the origin to the actual point itself. And we'll label that with the Greek letter rho. And then there's an additional angle we can look at, which is the angle that the positive z-axis makes with this ray right here. So that's that angle. We'll call that angle phi. And actually, let me also label this angle. This angle up here is also phi. So spherical coordinates consists of rho and phi and theta. And I should emphasize that the theta is the same theta as in cylindrical coordinates. But that r, this is not one of the spherical coordinates. It's just here kind of for reference to show us how spherical and cylindrical are related. So for starters, we'd like to know how to rewrite x and y and z in terms of these new coordinates. Z here, of course, is the distance of this dashed line right here. Well, we can use right triangle geometry to figure out the relationship between rho and z and r, because I have an angle of phi right here, and I have a right angle, which is this angle right here. Okay, so that means that rho represents the hypotenuse of this right triangle. So cosine of phi, then, is the length of the adjacent divided by the length of the hypotenuse. And so that implies that z is just rho times cosine of phi. Sine of phi is r, the opposite side, divided by rho, the hypotenuse. And so r is rho times sine of phi. And remember from last time, in cylindrical coordinates or polar coordinates, x you would normally write as r cosine of theta. And so since r is itself rho times sine of phi, you can think of x as being rho times sine of phi times cosine of theta. And in the same way, y is r times sine of theta, so rho sine phi sine theta. So these are the equations that let you convert from rectangular coordinates x, y, z to spherical coordinates in terms of rho, phi, and theta. And it's worth adding at least one more equation to this list, which is that since rho is the distance from the origin to the point x, y, z, that means that x squared plus y squared plus z squared is equal to rho squared. Okay, now let's look at these sort of angles a little bit more carefully, in particular at this angle phi, because this is the angle that tends to give people a little bit of trouble. Maybe it's helpful to draw a sphere. So you might imagine that you have a fixed rho value. So here's the center of the sphere. And in fact, I'm going to talk about this as if the sphere is really the Earth. So you have a North Pole and a South Pole, and you have the equator and so on. So that angle phi, let me again just sort of draw it right here. The idea is that if you have a point in space, then phi tells you the angle from that point up to the positive z-axis. So for example, phi equal to 0 means that your point is on the z-axis, on the positive z-axis, in fact. And that corresponds to being at the north pole of whatever sphere you're on. So we just sort of start counting the angle from 0. And now let me sketch in a line of longitude here. Right, so a line of longitude goes from the North Pole down to the South Pole. And basically, phi just tells you how far along that line of longitude you are, sort of how far down from the North Pole you are. Notice that this line of longitude is just half of a circle. So half of a circle, it has a range of 180 degrees, or pi radians. And so what will happen is that as you work your way down, well, sooner or later you're at the equator. And when you're on the equator, that's when you have traveled sort of 90 degrees down. You travel down an arc that is a fourth of a circle. So phi is pi over 2 at the equator. And then by the time you get to the South Pole, now you're looking at a phi value of pi. And actually, you can also see all of these algebraically. So remember that z is rho times cosine of phi. So what that means is that when phi is 0, that z is rho times cosine of 0. And since cosine of 0 is 1, you just get that z is rho. Right, so your z coordinate is rho, whereas your x and your y coordinates, well, they'll both be 0, because they both have a factor of sine of phi, which is going to be 0 when phi is 0. If phi is pi over 2, well, that means that z, which is rho times cosine of phi, now that's going to be 0. So you have a 0 z-coordinate, which means you're really kind of in the xy plane. Or if you're on a particular sphere, you're on the equator of that sphere, the intersection of that sphere with the xy plane. And if phi is equal to pi, well, now you get that z is rho times cosine of pi, which is negative rho. So that means that you're on the negative z-axis, and again, x and y will both be 0. So you can really kind of see the effect of phi completely algebraically this way. But here's the geometric way of how to think about it. And so let's talk about just the general range of these spherical coordinates. So for a full sphere, actually I should probably use the word ball. So in English, the word sphere can sort of interchangeably mean either the solid ball or just the surface of it. And in math, we try to be a little bit pickier. Usually, if you're talking about a sphere, you mean the surface. And if you're talking about a ball, you mean the actual solid. So let me call it a full ball of radius A. And we'll describe it using inequalities on the 3 spherical coordinates. To say that it's a full solid ball of radius A is to say that rho goes from 0 to A. Theta is the same as it was before. It measures how far around the z-axis you go. And if you want a full sphere, then you want 0 to 2 pi. Okay, so this is how far around the z-axis. And phi, we said, goes from 0 to just pi, right? And phi tells you, again, sort of how far down from the North Pole, or from the positive z-axis. So here's what you get for a full ball of radius A. And then if you want to start doing various halves of balls or other parts, well, then typically you'll restrict some of the angles here. So for example, let's say you want the upper half of this ball. By upper half, just to be very clear, I mean the positive z half. Well, that means that starting from the North Pole, you want to keep going until you hit the equator. And so in that case, phi goes from 0 to pi over 2, from the North Pole down to the equator. Okay, and so it turns out that for regions that are spheres or parts of spheres, well, spherical coordinates is kind of tailor-made for those regions. And so we'll see next time that when you want to integrate a function over such a region, you probably want to use spherical coordinates.